Welcome to Talkcast and to episode 203, if you're an audio-only listener. I do say that because if you go to my YouTube channel, there are additional episodes there that sometimes don't get uploaded to the audio-only podcast platform. So that's just by the by. But officially, this is episode 203 of Talkcast. This is also going to be the final part of Chapter 10, The Nature of Mathematics from the Fabric of Reality. As I've said before, going into the Fabric of Reality back in 1997, I remember the surprise I had at this chapter. I thought I'd understood the previous chapters. I had, but not particularly deeply, because what is in Chapter 10 simply follows from the preceding chapters, but it still comes as a surprise. This is why the idea of conjectural knowledge, why the ideas of Popper are so very deep. They profoundly change your view on absolutely everything you know, and that it is possible to know. I mean, when it came, as I often say, about Chapter 2, Shadows, that chapter is the most jarring of all the chapters I remember. Surprising and exhilarating. I think it's the most exhilarating piece of writing I've ever read, because at that time I was otherwise a confused physics undergraduate. And suddenly I was presented with an actual black and white, clear as day explanation. And I knew I was in the presence of an author who not only understood the physics, but also how to explain it in words that made sense to me. But in what followed, excited and exhilarated, and apparently worldview changing the epistemology and science was throughout the remainder of the book, the chapters on problem solving and criteria for reality, universality, justificationism, the centrality of explanation and fallibility. Fallibility, mind you, a term and concept David uses over and again before Chapter 10, it clearly had not quite sunk in for me. Not fully anyway. Because there I was in Chapter 10, where even up to this moment, it still had not struck me. I had been brought up in a culture where mathematics was a special subject. It was set apart from everything else. And of course, it is a special subject, but then history's a special subject, jiu-jitsu and tennis are special subjects, geography, geology, astrophysics, aeronautical engineering. I mean, they're all special subjects. But I was still under the misconception, as almost everyone who goes through school is, that mathematics was actually above, if not beneath, every single other subject. Apart, separate. It was certain, and it was pristine, clean, and could not possibly ever be doubted. So for all my thinking of myself as a newfound fallibilist, I still hadn't actually learned the lesson. It hadn't sunk in that mathematics, while yes, different, had something in common with all other knowledge. It was a domain where what we learned had been learned by us. Shocking, that. I mean, it does seem laughable in retrospect when you put it that way. Whatever we learn, it's we human beings that are learning it. Or we who encode our learnings into our machines, and our machines are error-prone as we are. Error is everywhere. Error is the natural state of things. It takes time, effort, energy, creativity to detect errors and then correct them and move forward. So there I was, reading the Fabric of Reality, getting up to Chapter 10, and not realizing that the full force of fallibility had not hit home for me. Not until this chapter, which is why it contains my most often referenced line, and why I put the chapter as number 2 on my favourite chapters from this book. Chapter 10 here only just gets edged out by Chapter 2, Shadows, but that's just an emotional bias, because with Chapter 2, I was simultaneously, as I read it, angry as I read the chapter, because why had my lecturers and tutors at university so confused me with nonsense and non-explanations and evasions? On the one hand, angry, and on the other hand, absolute elation that I now got it, I understood it. The world is understandable, comprehensible, and more amazing than any sci-fi fiction that I'd read or viewed had ever tried to show me. So, hitherto, mind you, and perhaps you're like me, when you think of the nature of mathematics, you think of words like truth and proof and certainty and necessity. Necessity is an important one that we'll certainly come to today. When studying philosophy, Leibniz, who by the way alongside Newton invented calculus, or at least is credited with inventing calculus, Newton and Leibniz were great rivals in this area. Well, Leibniz also wrote lengthy philosophical works. They were required reading, of course, for me as a philosophy student, unlike Popper. And I recall Leibniz's distinction that we would spend tutorials discussing. The distinction between necessity and contingency, its opposite, or possibility, if you like. Contingency is when things could have been some other way. It's not illogical to think of things as being in some other way. Often this is the realm of so-called many of the facts of science. Things could be different in other universes. What position the Earth happens to occupy in the solar system with respect to the sun could be different in another universe. There could be a universe out there where there's no Mercury, making Earth the second planet from the sun. There's nothing illogical thinking that way. It's just a contingent fact, a fact of happenstance. Mercury is not written deep into the laws of physics. The chances and pseudo-random motions of particles over billions of years that formed the universe and the galaxy and the gas clouds ultimately condensing into the sun and the solar system from previously exploded stars led to a quirky solar system that we now inhabit. It did not have to be this way. But on the other hand, once you define, say, a triangle as an enclosed figure with 3 straight sides, then it is literally impossible to sketch a 4-sided triangle. There's no contingency there. It's not possible that there are 4-sided triangles just waiting to be discovered out there somewhere or other. No, triangles necessarily have 3 sides. The internal angle sum of a triangle in 2 dimensions is 180 degrees if it's got straight sides. So there is this divide in the world. I kind of already knew this. I had a sense early on. Science generally explains what happens to be the case. Mathematics explains what must be the case, assuming a few things. Mathematics would be true no matter which universe you found yourself in. But geography, history, art, they're very much dependent on which universe you're in. They're dependent on what day you happen to wake up and which town you find yourself in. That's contingent on what else is going on at the time. So we can divide this world up, largely speaking, into the necessary and the contingent. Of course, there are necessary truths in science as well. If an atom contains 7 protons in its nucleus, then necessarily it's nitrogen. It does not matter where you find that atom. It could be on the other side of the universe, but nitrogen is defined as that element with 7 protons. There's no choice in the matter, no contingency, not anymore at any rate. As I hinted at in the last episode, what I've always liked about mathematics myself are the real basics, the absolute foundations, dig as deep as you can possibly get, the logic behind it, how even the simple assumptions can be overturned with a clever proof. When, and I guess this is apocryphal, early Greeks, Pythagoreans at first, thought all was number and so everything could be captured by rational numbers, fractions in other words, it came as a shock one day when someone drew this right triangle, 2 short sides of length 1 each. Well, what's the length of the hypotenuse? Well, you can use Pythagoras' theorem, which everyone who goes through high school does, and it's the square root of 2. What's the big deal about that? Well, the square root of 2 is not rational. It cannot be written as p over q, where p and q are integers with no common factor. The with no common factor restriction is absolutely essential. So let's actually go through this little proof, by the way. Reductio ad absurdum. Reaching a contradiction in our conclusion, in other words, which suggests that our initial assumption must have been false. So we have to begin with an assumption. Let's say you're a dogmatic Pythagorean and insist any number whatsoever, any length, anything, whatever in the universe can be represented by a fraction, p over q, where p and q are in their simplest form, which means there's no common divisor of p and q. For example, 1 over 3. 1 and 3 have no common divisor. If we had 2 over 6, then this would fail our test, because then the numerator and the denominator do indeed have a common factor, 2. So we would take our 2, divide it through 2 over 6 and end up with 1 over 3. So remember that from school? Okay, so let's begin with our assumption. Assume it is indeed possible to write root 2 equal to p over q, where p and q have no common factors. Let's grant the Pythagoreans, the early Pythagoreans, their assumption. Okay, we've got root 2 equals p over q. What follows? Well, let's square both sides. And the square of root 2 becomes 2. and the square of p over q becomes p squared over q squared. Let's call that equation 1. Let's multiply both sides of this equation by q squared, so we get 2q squared equals p squared. And because p squared now equals something multiplied by 2, that means p squared is even. It's a multiple of 2. But if p squared is even, like the number 16, then so too is its square root p, 4, is also even. So there we go. Given p is even, we can then rewrite p as being 2r, 2 times any number that you like. Multiply any number, the simple integer, by 2, and you'll get an even number. In other words, p is a multiple of 2. All right, let's continue. Let's substitute that fact, p equals 2r, where r is any integer you like, back into the equation that we just labelled number 1. So 2 equals 2r squared, all of that squared, all over q squared. As before, we're going to multiply both sides of the equation by q squared to get 2q squared equals 4r squared. Expanding all of that out. Divide through by 2 to get q squared equals 2r squared. And now we find by the same argument, q squared must also be even. It's also a multiple of 2, so therefore q, by the same logic, is even. Q is equal to 2t, where t is any integer that you like. So if q is even and p is even, they're both multiples of 2, our very first assumption that the square root of 2 equals p over q, where p and q have no common factors, was false all along. We simply cannot write root 2 as a rational number. Hence, it cannot be written as p over q. It's not a fraction. It cannot be written as a simple fraction. It's an irrational number. It's little proofs like that that make mathematics a lot of fun. You start out counting integers and you realize, okay, so that's important to be able to do. You want to be able to count stuff in order to calculate things. Maybe you want negative numbers as well to realize when people go into debt or when you have less than nothing and you owe someone else something. Maybe you don't have a whole thing, so you've just got a fraction of something. But then this rich area of mathematics opens up with a proof like this, where you find that there are even some numbers that can't be written as fractions. That's pretty cool. I find these little proofs puzzles in a way that reveals something deep for us to glimpse about the surprising structure of mathematics. Like, even the number 1 itself can be endlessly fascinating. I mean, there is this numeral that we use that I put on the screen, 1, that everyone's familiar with, that we commonly refer to as 1. But, 2 over 2 is also equal to 1. Pi over pi is equal to 1. O-N-E, that's 1. Okay, all these different ways of representing this number 1 are different numerals, different instantiations of the number 1. Taking that number, that abstract quantity, and putting it into something physical. A surprising one that people really struggle with is that 0.9 recurring is 1. 0.9 recurring is 0.9 with a little dot on the top, or 0.99999999999, where the 9s just go on literally forever. That's also equal to 1. And even after they see the proof, many people are still balked by the whole thing and refuse to admit that the proof is actually a proof. The proof only goes for 4 or 5 lines. Like, assume x equals 0.9 recurring. Okay. Let's multiply both sides of that by 10. Multiply through by 10. Well, 10x equals 9.9 recurring. 9.999999999. Well, then what's 9x? Well, 9x is what you get when you take 10x and you subtract x. So 10x take away x means 9.9999 recurring, take away 0.9999 recurring. So the 0.9 recurring part cancels each other out. That gets subtracted from the 9.9 recurring. So you're left with 9x equals 9. 10x take away 1x is 9x. 9x equals 9. In other words, x equals 1. But you began with the assumption that x equals 0.9 recurring. And you've proved that 0.9 recurring also happens to equal 1. There's no deep mystery here. These are just different ways of representing, using symbols in physical objects, how these numbers, in this case 1, can be represented in different physical forms. We can put together all sorts of fancy mathematical symbols that are equivalent to this number 1. ways of representing this number one, ways of understanding what this number one actually is, this abstract thing that we can never actually capture, we can only represent. We can't perceive it directly. We can't understand it completely. Have we just contradicted ourselves in that proof? No, we've just proved that this thing, one, can be represented in forms that look radically different. The difference between a finite string, one, boring, and an infinite string of nines in 0.99999 off to infinity, or off to one, if you like, it reminds me of the distinction we've made before on Topcast and elsewhere about how there are more numbers between 0 and 1, more real numbers, than there are between 0 and all the counting integers, counting them one at a time. So starting at 1, 2, 3, 4, 5. At least you're able to count them. They're countable. There's a place to start. Start at 0 or 1 and then proceed to the next one, 2, 3, 4, by adding 1 each time. That's countable. But between 0 and 1, well, okay, start at 0. Where do you go next? What's the next smallest number? Well, it's not 0.1 because there's something smaller than that, 0.0001, 0.000001. There's nowhere to even start. It's impossible to begin the counting process. It's an uncountable infinity. Another surprising piece of mathematics. And anyone who has listened to the previous episodes on this chapter, or chapter 5, the reality of abstractions from the beginning of infinity, will know that I've mentioned some of this before. And all of these little surprises sort of pale in comparison, I would say, to the surprise we encounter here towards the end of the chapter. Because none of what I've just said seems to rule out certainty or firm foundations. They're just surprising results about things of which we can be certain, aren't they? Well, I think everyone who watches and listens by now knows my position on certainty. Certainty is just an emotion. It's subjective. It's a stance one can have or take towards a particular claim. But it's got nothing to do objectively with the truth of any claim. Be as certain as you like. I mean you, not me. I'm happy with uncertainty. I like knowledge, and knowledge is enough when it's a good explanation. Good, that is, to me. I don't have to be certain of it. It solves my problem. There's just no other option when it happens to be a good explanation. But Brett, if you're not certain you'll die, why not just leap off a tall building then? Because after all, you think there's a chance you'll survive. Well, no. I know that I'll die if I leap off a tall building. Aha, the interlocutor often says, there you go, you're certain after all. No. I just know I'm not certain. I could be wrong, but you do you, as they say. People want certainty. And when I was reading this chapter, again, for the first time back in 1997, I was still stuck with mathematics is about certainty. And when I was reading this chapter all the way back in 1997, as I kept on saying, I was still stuck in this place where mathematics is about what would certainly be the case. There was no doubt there. If something was proved, it was proved true and proved for all time, or proved false. How could it be otherwise? I can't imagine. No one can imagine. There cannot possibly be a flaw with this thing. It's been proved. Mathematics is on solid ground. Mathematics is the solid ground. It's how physics is held up a little bit higher. It's a more emergent sort of a subject. There's that hierarchy, remember? Mathematics, the rock-solid certain foundation. Science, a domain of claims where we can be highly confident as we gather more and more evidence. And, well, history, philosophy, morality, well, those depend upon your perspective and culture, right? So it was said. Of course, this is all a subtle shift many struggle to make. It's like one small step for man, but one giant leap for the mind. Just admit the possibility of error everywhere. The possibility, not the necessity. Look, I have no reason to doubt that 1 + 1 = 2, as the trope example goes, or that the natural numbers continue without limit, or that the decimal expansion of pi does not go on forever. No reason to doubt any of it, or that Earth is the third planet from the sun for that matter, or that World War II happened in the way that the traditional textbooks tend to say it did. But I remain a fallible human being, just like everyone else, a person. I make mistakes. So although I can't imagine how 1 + 1 = 2 could be wrong, well, I just know I've also got a limited imagination. Does this prove 1 + 1 does not equal 2? Of course it doesn't. 1 + 1 = 2. But I do not have to say, therefore, on the basis that I've got no reason to doubt it, that mathematics is different in kind because I, Brett Hall, nor anyone else, nor anyone I've ever known, ever claims to doubt it. 1 plus 1 equals 2, or the internal angle sum of a regular triangle is 180 degrees. But, for centuries, people barely doubted Newton's law of gravitation. Physicists were elated that they had it. The law, the final word. It's how religious people today must feel about their holy books, at least some of them. Thank the Lord we've been given this. Something inerrant, something not to be doubted. They want the book, or the leader, or the foundation. Some place like Archimedes to anchor their worldview to and to be able to compare everything else to. That is the mistake that the truth can be manifest. That you can see truth in the world, whether in a holy book or a not so holy book, or in a mathematical proof or a scientific mathematical foundation, that the truth, the final truth, can be found. Some people really seem to need that. The starting point, which really is an end point more than a start. It's the thing that cannot possibly be understood better or more deeply. It cannot be improved. It is, after all, the inerrant truth that you know for certain. And on 1 plus 1 equals 2, by the way, and I know I've made this point before as well, you can do the proof. Yet another useful exercise from university days, starting from Peano's axioms and defining 1 as the first integer and the successor of 1 as what you get by adding the first integer to 1 and addition as this operation, and so on and so forth. And after about an A4 page of logic, depending upon how rigorous you're being, you can prove 1 plus 1 equals 2. And I remember seeing this in a lecture, and the lecturer then saying, now your homework is to prove that 2 plus 1 equals 3. So you can see these things more deeply. You can come to understand the very basics at a deeper level, realizing you had certain misconceptions. I had misconceptions about the basics. It didn't prove there was anything wrong with 1 plus 1 equals 2, but it did suggest I could understand things more deeply if I delved more deeply into certain subjects.
The dwarves delved too greedily and too deep.
The point is, we don't need certainties, even in mathematics. As Karl Popper says, quote, the doctrine that the truth is manifest is the root of all tyranny, end quote. And the tyranny is everywhere, from the most dangerous political and religious fanatical ideologies through to tyrannies of the mind where one thinks, well, this is the truth, so no need to think of any alternative. These subtle shifts from being someone who is a believer or someone who is pursuing the final, certain, ultimate truth, instead to someone who is trying to create conjectural explanatory knowledge, makes all the difference to the way in which we see the world, see each other, the possibility for progress. I'm going to get to the readings very shortly. David has been writing, up until this point, about, among other things, of course, Roger Penrose, the great mathematician who is interested in the intersection between computation, mathematics, physics, and consciousness, and thinks there is some connection of the results, for example, between Gödel and other mysteries. Mysteries, for now at any rate, like consciousness. Like David, I'm sceptical of the project. I put it in a similar bucket to the pioneers of quantum theory who saw consciousness as having a fundamental part to play in the explanation of interference experiments. Look away and the universe is wave-like, look at it and it becomes particles all over again. As it turns out, no, that was all a mistake. It never seemed plausible to begin with. But, people still today think that there is this deep connection between the observed and the observer. They're connected, but they're also separate. The observer is somehow obeying different physical laws, collapsing wave functions and so on. Gödel's result likewise, spectacular and interesting, like quantum theory. Both hint at something deeply counterintuitive. But a deep mystery over there in how the physics or mathematics of the world is operating, and a deep mystery over there, what consciousness is, do not sum together to a solution, much less a good explanation. Consciousness is a genuine mystery. Quantum theory is counterintuitive. But it doesn't say what consciousness is. Quantum theory doesn't. It's silent on the matter. We cannot even formalize what we mean by that string of characters, consciousness. But Penrose hopes to link consciousness to Gödel in some way. On this, David writes, quote, anyway, Penrose hopes for a new fundamental theory of physics, replacing both quantum theory and the general theory of relativity. It would make new testable predictions, though it would of course agree with quantum theory and relativity for all existing observations. There are no known experimental counterexamples to those theories. However, Penrose's world is fundamentally very different from what existing physics describes. Its basic fabric of reality is what we call the world of mathematical abstractions. In this respect, Penrose, whose reality includes all mathematical abstractions, but perhaps not all abstractions, like honour and justice, is somewhere between Plato and Pythagoras. What we call the physical world is, to him, fully real, another difference from Plato, but is somehow part of or emergent from mathematics itself. Furthermore, there is no universality. In particular, there is no machine that can render all possible human thought processes. Nevertheless, the world, especially of course its mathematical substrate, is still comprehensible. Its comprehensibility is ensured not by the universality of computation, but by a phenomenon quite new to physics, though not to Plato. Mathematical entities impinge directly on the human brain, via physical processes yet to be discovered. In this way, the brain, according to Penrose, does not do mathematics solely by reference to what we currently call the physical world. It has direct access to a Platonic reality of mathematical forms and can perceive mathematical truths there with, blunders aside, absolute certainty. End quote. Well, one might well wonder how we can put blunders aside. We cannot, of course. They're baked in. The thing about mathematics and science is, it works. It actually underpins the reason why we see the objective improvements in the world. Progress, in other words. But why denying the universality of computation is required in order to shore up one's theorems in mathematics, I don't know. I think it's an unnecessary step, but we'll see what David has to say as we move through this chapter on this. The fact is, the brain is just made of matter. Yes, it's complex, but these ideas that mathematical truths impinge upon the human brain via some yet-to-be-discovered physical process, it sounds woo. And of course, Penrose is the furthest thing from woo that you can assume. But my thought is, if you have a good explanation, which the universality of computation is, go as far as you possibly can with that. And it does explain why mathematics works, why we can uncover knowledge about mathematics, and why sometimes we make mistakes. In other words, why the blunders come as part of the package, whatever the case. David goes on to say, quote, "It is often suggested that the brain may be a quantum computer, and that its intuitions, consciousness, and problem-solving abilities might depend on quantum computations. This could be so, but I know of no evidence and no convincing argument that it is so. My bet is that the brain, considered as a computer, is a classical one. But that issue is independent of Penrose's ideas. He is not arguing that the brain is a new sort of universal computer, differing from the universal quantum computer by having a larger repertoire of computations made possible by new post-quantum physics. He is arguing for a new physics that will not support computational universality, so that under his new theory, it will not be possible to construe some of the actions of the brain as computations at all." End quote. Yes, one can always go down this route. It's exactly like the dark energy problem. You can say, well, we just need new physics for this, rather than saying, perhaps there's just something we don't understand here that will be able to be understood in light of new observations that fit within the framework of quantum theory and general relativity. It could be that we need to overthrow our ideas about Big Bang inflation. It could be that. It could be that there's something wrong fundamentally with our understanding of quantum theory. But that rejection of a good explanation is not itself an explanation. So Penrose's rejection of the universality of computation and saying that we need new physics in order to understand how the brain is able to understand mathematics is not itself an explanation. It seems to be more an emotional reaction against the universality of computation. It's a rejection of the best explanations we have within physics. All physical processes can be considered as computations. They can be simulated. I mean, to arbitrary accuracy. Of course, that could be false. But absent a better explanation, refuting our best known explanation that I've just told you, computational universality, just go with computational universality for now and see how far it can get you. Unless you do have an actual better explanation. It's kind of like, I guess, creationists who like to find issues with evolution by natural selection, like here's a missing link or here's something that can't quite be explained. Well, okay, there's a problem there, but we've got no alternative. Should we throw out all of neo-Darwinism in favour of creationism because you've found a problem which all biologists agree is a problem, it isn't understood well yet? This is always the case in science. This is the open-ended nature of science. But I don't see a particular problem here. We have got a problem with what is consciousness. But saying we need a new physics for this, well, maybe we do. But that itself is not even a research program, much less a good explanation. I'm skipping a substantial part now, and I'm picking it up where David says, quote, "I have presented only a sketch of the arguments of Penrose and his opponents. The reader will have gathered that essentially I side with the opponents. However, even if it is conceded that Penrose's Gödelian argument fails to prove what it sets out to prove, and his proposed new physical theory seems unlikely to explain what it sets out to explain, Penrose is nevertheless right that any worldview based on the existing conception of scientific rationality creates a problem for the accepted foundations of mathematics, or as Penrose would have it, vice versa. This is the ancient problem that Plato raised, a problem which, as Turing points out, becomes more acute in the light of both Gödel's theorem and the Turing principle. It is this: in a reality composed of physics and understood by the methods of science, where does mathematical certainty come from? While most mathematicians and computer scientists take the certainty of mathematical intuition for granted, they do not take seriously the problem of reconciling this with a scientific worldview. Penrose does take it seriously, and he proposes a solution. His proposal envisages a comprehensible world, rejects the supernatural, recognizes creativity as being central to mathematics, ascribes objective reality both to the physical world and to abstract entities, and involves an integration of the foundations of mathematics and physics. In all those respects, I am on his side." End quote. And of course, so am I. And as we will come to, the resolution, spoiler alert, is that this desire for mathematical certainty is really the problem. The intuitionists had the idea that if you can intuit something as being certain, this is Descartes' error as well, if it's self-evidently true, then you've proved it because it's self-evident. How could it be otherwise? If you can't possibly doubt the thing, then that thing that is unable to be doubted must be true. But as I like to say, that could just be your lack of imagination. That's not ruling out fallibility, it's proving fallibility, if anything. Any thought you have could be wrong. And you can't escape from that. You're trapped inside the darkness of your mind, gathering scant bits of evidence and trying to interpret them. That's our situation. You're not being fed the truth. You can believe that if you like, but that's going to lead you into error, an egregious error at times too. Very dangerous place to be, to think you possess the truth when in fact you do not. And also it leaves you open to a certain kind of pessimism because you don't think that certain things can be improved. But David goes on, I'm skipping a part here, to talk about a little about geometry. In geometry, we talk about ideals, Platonic ideals, as we say, especially the ideal circle. How can we understand perfect circles? If we don't have access to perfect circles, we've only got access to imperfect circles, things that we draw with pencil and paper and on computers, represented by physical stuff. And physical stuff is imperfect, it's not abstract. So how can we get from this imperfect physical representation to some truth about the abstract thing? How does that work? Well, David explains, quote, "The reliability of the knowledge of a perfect circle that one can gain from a diagram of a circle depends entirely on the accuracy of the hypothesis that the two resemble each other in the relevant ways. Such a hypothesis, referring to a physical object, the diagram, amounts to a physical theory and can never be known with certainty. But that does not, as Plato would have it, preclude the possibility of learning about perfect circles from experience. It just precludes the possibility of certainty. That should not worry anyone who is looking not for certainty, but for explanations." End quote. Isn't that beautiful? I mean, what we've got summed up there in just that paragraph, and especially the last sentence, is an encapsulation of the entire worldview of Karl Popper and especially David Deutsch. It doesn't matter that you're not certain about something. What we want is knowledge, and knowledge can be divorced from certainty. In fact, it's the uncertainty that allows us to realize that no matter how confident we are about something, whatever our emotional attachment is to a particular thing, that nevertheless, there could be some error there. And that's exciting because it means we can correct the error and improve our circumstance. Even if we think we've got the best, something better might yet be on the horizon. So I'll just say it again. Let me just read that little bit again. The final sentence. That should not worry anyone who is looking not for certainty, but for explanations. Beautiful. We move from our physical world of books and computers and pens and paper into an abstract world of mathematics by linking the two with explanations. Not because those explanations are certain, but because they allow us to solve problems as they arise, giving us an ability to glimpse what that abstract world is like. In the same way that we're able to glimpse what the interior of a star is like, even though we'll never get there, and we'll never send a probe there, nothing like that, through our explanations of what nuclear fusion is and what's happening many light years away from us. Mathematics, in a sense, resembles what's going on in science because we don't see ultimate reality in either case. What is the deepest part of reality, what the actual fundamental particles are when it comes to, let's say, particle physics. Is the electron fundamental? Is the photon fundamental? Or are there constituent parts in those things? Well, at the moment, we think they're fundamental, but this doesn't rule out learning more about these things as time goes on. Perhaps they won't turn out to be fundamental. They'll be smaller particles still. But in any case, we don't have to be certain that at any point in time we have the final answer in science or mathematics or anywhere else. What we want are explanations, and explanations that we can improve and allow us to solve our problems. David goes on to say, quote, Euclidean geometry can be abstractly formulated entirely without diagrams, but the way in which numerals, letters, and mathematical symbols are used in a symbolic proof can generate no more certainty than a diagram can, and for the same reason. The symbols, too, are physical objects, patterns of ink on paper, say, which denote abstract objects. And again, we are relying entirely upon the hypothesis that the physical behaviour of the symbols corresponds to the behaviour of the abstractions they denote. Therefore, the reliability of what we learn by manipulating those symbols depends entirely on the accuracy of our theories of their physical behaviour and of the behaviour of our hands, eyes, and so on with which we manipulate and observe the symbols. Trick ink that caused the occasional symbol to change its appearance when we were not looking, perhaps under the remote control of some high-technology practical joker, could soon mislead us about what we know for certain, end quote. Now, this is where, as I've used this phrase before, the vertigo begins to set in, where the floor beneath your feet begins to fall away. This was the first part, I think, before I get to the real punchline, of course, of the chapter. But this is where it first began, the scales fall from one's eyes, as they say. It began to dawn on me, this right here, because I knew, hold on, trick ink? We don't need trick ink. Ink is already tricky enough. It's made of matter, and matter obeys the laws of quantum theory, and those have uncertainty baked in. This is why I say, hold on, the sense of vertigo, whoa. Everything that we understand about mathematics comes to us by reading symbols on paper or on a screen. Those symbols, that ink, those pixels, whatever it happens to be, are obeying physical laws. But we've already learned the physical laws mandate the possibility of error. Our learning, our understanding, our knowledge of mathematics, therefore, is only ever as certain as what we understand the laws of physics to be. And those laws of physics tell us that uncertainty is everywhere, all the time. And it's not an emotional kind of uncertainty. It's nothing to do with that. This is a physical bound upon what can be known, or certain of. And those who tend more in the direction of mathematics than in physics get upset at this. I've encountered this personally, because it is physics that places a barrier on what can be known even in mathematics. Even in mathematics. And never mind just what's going on paper, with so-called trick ink, or just regular ink, which might be obeying the laws of physics, which causes one symbol to change into another symbol, a 0 to become a 1, a high potential to become a low potential, whatever. Neurons in brains, that's matter as well. Every human who ever existed may very well have proved the same thing over and over again without a problem, but what does that matter either? Truth is not a matter of consensus. Certainty, at this moment of reading this book right here, was quickly becoming uncertain for me. And so it was exciting, it was exhilarating, because I knew that David was never going to go to relativism. I knew that that was ruled out. That had already been ruled out earlier. And that is the problem, though, that sometimes there are books, nothing, of course, is in this league, but people do reach the realization there can be no certainty. And so what do? Well, they take one of two paths. In general, they become relativists, especially in the area of morality, but they become relativists across the board. Well, if you can't be certain, then you can't know anything, so therefore all hope is lost. Everyone's just inside of their own heads with their own truth. You have your truth, I have my truth, and, well, let's just try and get along. And of course, in that situation, no one ever does. There is a truth, and we can all come to understand it to a better or worse degree. We can make progress. We can solve problems. We can have meetings of minds. Relativism is completely false. It's as bad, or a species of, dogmatism. Those people who think they already have the truth, the certain truth, in hand now. We don't need to go into either direction. We do not need to begin with, the law of identity, A equals A. We don't have to start there. We don't have to start anywhere. We don't have to reject all truth either. Instead, we can say, truth exists, and the purpose of knowledge is to come to understand something about our circumstance, to solve our problems, to make progress, to move forward, to objectively rule out some explanations as being worse than others. And in the future, identify errors, correct errors, and make everything better. And come to some agreement to some extent, while realizing that we're always going to disagree because we're going to have different perspectives. But there is one actual physical reality out there, and abstract reality as well, by the way, which we can use in order to improve the universe, everything, for people. That's why we're here, to solve our problems. I'm skipping some more substantial passages. I recommend you read the entire chapter yourself, of course. David talks about the possibility of actually perceiving perfect circles in virtual reality. So I'm going to skip over that, and I'll pick it up just with one paragraph here where David writes, quote, "Incidentally, Plato's idea that physical reality consists of imperfect imitations of abstractions seems an unnecessarily asymmetrical stance nowadays. Like Plato, we still study abstractions for their own sake, but in post-Galilean science and in the theory of virtual reality, we also regard abstractions as means of understanding real or artificial physical entities. And in that context, we take it for granted that the abstractions are nearly always approximations to the true physical situation. So whereas Plato thought of earthly circles in the sand as approximations to true mathematical circles, a modern physicist would regard a mathematical circle as a bad approximation to the real shapes of planetary orbits, atoms, and other physical things," end quote. So that's marvellous. Now remember, there is one reality, as I like to say, but we can partition up this reality into different kinds. We can have the physical stuff, which consists of the atoms and the planets and whatever else. And then we can have the abstract stuff, which is the numbers and concepts like justice and so on and so forth. Does this make me a dualist? I don't think so. I don't know. I don't know what dual means, but if I think there are positive and negative numbers, does that make me a dualist? I don't know. Maybe it does. But the thing is, we can regard abstractions as sometimes the approximation to what is really going on in the physical world, or vice versa. We can say, okay, well, these physical things, these numerals, represent numbers, which are the ideal abstractions, which we do not have access to, but we can glimpse something about by manipulating the symbols. And what David also says there as how it was taken for granted that the abstractions are nearly always approximations to the true physical situation echoes his more recent remarks on propositions, which are these things that exist in logic and in mathematics, represented by symbols, which have truth values, but we can't actually utter them. All we can do is represent them. And statements as a matter of logic, which are at best approximations to propositions. So in logic, we manipulate these propositions, P and Q for example, in order to prove some logical sequence follows, a conclusion follows from given premises using the rules of inference. Those are propositions. But the propositions just represent some arbitrary statement. And the arbitrary statement is, Socrates is a man. But that's not a proposition itself. It's an approximation to a proposition. Only propositions have, strictly speaking, truth values, can be true or false, strictly speaking. But we can understand something about the logical structure of the physical world and the abstract world by invoking the notion of propositions and formal logic and formal mathematics and pure mathematics. Pure mathematics is going to tell us something about, at times, the narrow areas where the pure mathematics has something to do with the physical world. Skipping another substantial part, and I'm picking it up where David says, quote, "Using a perfect virtual reality rendering, we might experience 6 identical circles touching the edge of another identical circle in a plane without overlapping. This experience, under those circumstances, would amount to a rigorous proof that such a pattern is possible, because the geometrical properties of the rendered shapes would be absolutely identical with those of the abstract shapes. But this sort of hands-on interaction with perfect shapes is not capable of yielding every sort of knowledge of Euclidean geometry. Most of the interesting theorems refer not to one geometrical pattern, but to infinite classes of patterns. For example, the sum of the angles of any Euclidean triangle is 180 degrees. We can measure particular triangles with perfect accuracy in virtual reality, but even in virtual reality, we cannot measure all triangles, and so we cannot verify the theorem. How do we verify it? We prove it. A proof is traditionally defined as a sequence of statements satisfying self-evident rules of inference. But what does the proving process amount to physically? To prove a statement about infinitely many triangles at once, we examine certain physical objects. In this case, symbols, which have properties in common with whole classes of triangles. For example, when under appropriate circumstances we observe the symbols triangle ABC is congruent to triangle DEF, we conclude that a whole class of triangles that we have defined in a particular way always have the same shape as corresponding triangles in another class which we have defined differently. The appropriate circumstances that give this conclusion the status of proof are, in physical terms, that the symbols appear on a page underneath other symbols, some of which represent axioms of Euclidean geometry, and that the pattern in which the symbols appear conforms to certain rules, namely the rules of inference." End quote. Pausing there for a moment. So, just notice, and I was under this misapprehension for decades, until I left school, that if something was proved in mathematics, then it was proved true. Subtle shift. If something is proved in mathematics, it just means that it follows from the premises. But how do you know the premises are true? Well, usually the answer that's given is they are self-evidently true. How could they be otherwise? Well, okay, but people can make mistakes. And there's all sorts of examples where, the axiom of choice, for example, where people aren't exactly sure whether or not certain axioms should be included. And you can have different axiomatic systems in order to solve different kinds of problems. The point is, what is self-evident to one person may not be self-evident to someone else. So what is self-evident? What is the standard? And that's too subjective. Better to just say what's going on in mathematics with a proof is that if the axioms are true, and if your rules of inference are valid, then what you'll get at the end, your conclusion, is also true, on the assumption the axioms are true. You don't even need to say that. You can just say it's proved. Following the conclusion follows from the axioms. It has been proved. True, false, doesn't matter. It's been proved. Proof is a mechanical, computational, physical process. David goes on to write, quote, "But which rules of inference should we use? This is like asking how we should program the virtual reality generator to make it render the world of Euclidean geometry. The answer is that we must make use of rules of inference which, to the best of our knowledge, will cause our symbols to behave in the relevant ways like the abstract entities they denote. How can we be sure that they will? We cannot. Suppose that some critics object to our rules of inference because they think that our symbols will behave differently from the abstract entities. We cannot appeal to the authority of Aristotle or Plato, nor can we prove that our rules of inference are infallible. Quite apart from Gödel's theorem, this would lead to an infinite regress, for we should first have to prove that the method of proof we have used was itself valid. Nor can we haughtily tell the critics that there must be something wrong with their intuition, because our intuition says the symbols will mimic the abstract entities perfectly. All we can do is explain. End quote. Quite right. All we can do is explain. There's no point hurling intuitions at each other. There's no point saying that your standard for proof and truth is superior or lesser than mine. All we can do is explain to each other, to engage in a discussion, to try and come to a mutual understanding of who in fact has the rules of inference that are able to get the job done, solve the problem, complete the proof. Skipping another couple of paragraphs, and David goes on to write, quote, "A conventional symbolic proof seems at first sight to have quite a different character from the hands-on virtual reality sort of proof. But we see now that they are related in the way that computations are to physical experiments. Any physical experiment can be regarded as a computation, and any computation is a physical experiment." Okay, I'm going to read that again because that's amazing. Experiments and proofs. We see now that they are related in the way that computations are to physical experiments. Any physical experiment can be regarded as a computation, and any computation is a physical experiment. David goes on. In both sorts of proof, physical entities, whether in virtual reality or not, are manipulated according to rules. In both cases, the physical entities represent the abstract entities of interest. And in both cases, the reliability of the proof depends on the truth of the theory that physical and abstract entities do indeed share the appropriate properties. We can also see from the above discussion that proof is a physical process. In fact, a proof is a type of computation. Proving a proposition means performing a computation which, if one has done it correctly, establishes that the proposition is true. When we use the word proof to denote an object, such as ink on paper text, we mean that the object can be used as a program for recreating a computation of the appropriate kind. It follows that neither the theorems of mathematics, nor the process of mathematical proof, nor the experience of mathematical intuition confers any certainty. Nothing does. Our mathematical knowledge may, just like our scientific knowledge, be deep and broad. It may be subtle and wonderfully explanatory. It may be uncontroversially accepted, but it cannot be certain. No one can guarantee that the proof that was previously thought to be valid will not one day turn out to contain a profound misconception, made to seem natural by a previously unquestioned, self-evident assumption either about the physical world or about the abstract world or about the way in which some physical and abstract entities are related." End quote. There is no royal road to truth. There is no way of inherently getting to certain knowledge. Knowledge is good enough. It is that which solves a problem for you. It is useful information that is copied over time. And so much of mathematics consists of this kind of knowledge, explanatory and solving a problem. We don't need to go around doubting it all as being on foundations that are insufficiently solid. We just don't need to worry about that. If our problems are being solved, if we're improving, if we're making progress, if we're explaining the world ever better, improving on what we knew yesterday by building something new tomorrow, that's good. We're correcting errors. We're making the world a better place. That's what we're after, not certainties. Certainty is a chimera. It's the wrong goal to have. The final ultimate truth doesn't need to be worked towards. Instead, what we want is understanding, comprehension, explanation. That's it. David goes on to say, skipping again a few more paragraphs, quote, "A very similar misclassification has been caused by the fundamental mistake that mathematicians since antiquity have been making about the very nature of their subject, namely that mathematical knowledge is more certain than any other form of knowledge. Having made that mistake, one has no choice but to classify proof theory as part of mathematics, for a mathematical theorem could not be certain if the theory that justifies its method of proof were itself uncertain. But as we have just seen, proof theory is not a branch of mathematics. It is a science. Proofs are not abstract. There is no such thing as abstractly proving something, just as there is no such thing as abstractly calculating or computing something. One can, of course, define a class of abstract entities and call them proofs, but those proofs cannot verify mathematical statements because no one can see them. They cannot persuade anyone of the truth of a proposition any more than an abstract virtual reality generator that does not physically exist can persuade people that they are in a different environment, or an abstract computer can factorize a number for us. A mathematical theory of proofs would have no bearing on which mathematical truths can or cannot be proved. In reality, just as a theory of abstract computation has no bearing on what mathematicians or anyone else can or cannot calculate in reality unless there is a separate empirical reason for believing the abstract computations in the theory resemble real computations. Computations, including the special computations that qualify as proofs, are physical processes. Proof theory is about how to ensure those processes correctly mimic the abstract entities they are intended to mimic. End quote. Wow, that's an inspired piece of writing as well there. Proof theory is a science. In order for something to be proved, there needs to be a prover, a mathematician or a computer. In any case, this prover, this thing that does the proving, obeys physical laws. Physical laws are part of science. That's the domain of science to understand. So if you want to have an understanding of mathematics, the certainty of mathematics, the certainty of the conclusions of mathematics, you better first realize that what you're doing is something physical. Performing the act of proving something is to perform a calculation, is to perform a computation. Computations require a computer, computers are made of matter, matter obeys the laws of physics. You can't escape from this. You're stuck in the real physical world. That real physical world allows you to glimpse something about the fact that there is more than just atoms moving in a void. There are these abstract things called numbers. Some abstract numbers are so vast they can't possibly be represented in the physical world, but they exist. Where do they exist? Wrong question. You're asking for a space in physical space for the abstract world to exist, but that's the wrong question. Abstractions are abstractions precisely because they are representative of a class of things that may or may not exist physically, but which we conjecture. David goes on to say, quote, Gödel's theorems have been hailed as the first new theorems of pure logic for 2,000 years. But that is not so. Gödel's theorems are about what can and cannot be proved, and proof is a physical process. Nothing in proof theory is a matter of logic alone. The new way in which Gödel managed to prove general assertions about proofs depends on certain assumptions about which physical processes can or cannot represent an abstract fact in a way that an observer can detect and be convinced by. Gödel distilled such assumptions into his explicit and tacit justification of his results. His results were self-evidently justified, not because they were pure logic, but because mathematicians found the assumptions self-evident. One of Gödel's assumptions was the traditional one that a proof can have only a finite number of steps. The intuitive justification of this assumption is that we are finite beings and could never grasp a literally infinite number of assertions. This intuition, by the way, caused many mathematicians to worry when, in 1976, Kenneth Appel and Wolfgang Haken used a computer to prove the famous four-colour conjecture, that using only four different colours, any map drawn in a plane can be coloured so that no two adjacent regions have the same colour. The program required hundreds of hours of computer time, which meant that the steps of the proof, if written down, could not have been read, let alone recognised as self-evident by a human being in many lifetimes. Should we take the computer's word for it that the four-colour conjecture is proved? The skeptics wondered, though it had never occurred to them to catalogue all the firings of all the neurons in their own brains when they accepted a relatively simple proof. End quote. Yeah, that example of the proof of the four-colour conjecture, I don't see that it is any more mysterious than a lot of the mundane calculations that are done by physicists as a matter of routine when you're performing vast calculations, the simulations that go on, for example, where you crash galaxies together. No one could ever possibly do that calculation without a supercomputer. But there's no reason to presume that the supercomputer is completely mucking everything up and getting it completely wrong. I mean, it could be, but just because you're not able to check it by hand doesn't mean there's anything less reliable about it. Why are human neurons especially good where silicon computers are not? I think that we use these things as tools as we use pocket calculators as tools. And insofar as we understand the relationships between the electronic circuitry or the programming of the computer and what we're trying to use the thing for, that's enough. Okay, we have an explanation linking the reliability of the output of the computer to what we actually want it to achieve. Proof or calculation, whatever. Skipping a little, and David goes on to the parable of Achilles and the tortoise. This is the idea of, is space infinitely divisible? If I want to, pick up my phone here, do I first have to go half the distance, then half the distance again, half the distance again, half the distance again, ad infinitum? How can I possibly ever pick anything up? Because there's an infinite number of points between me and the phone, and yet I do it. How do we resolve this kind of paradox? Well, on this. If the tortoise has a head start on Achilles, then if Achilles tries to get where the tortoise was, then it will have moved a little further ahead. And so each time Achilles tries to catch up, the tortoise will have gotten a little further ahead. How does Achilles ever overtake the tortoise? David writes, quote, "But what Achilles can do cannot be discovered by pure logic. It depends entirely upon what the governing laws of physics say he can do. And if those laws say he will overtake the tortoise, then overtake it he will. According to classical physics, catching up requires an infinite number of steps of the form move to the tortoise's present location. In that sense, it is a computationally infinite operation. Equivalently, considered as a proof that one abstract quantity becomes larger than another when given a set of operations is applied, it is a proof with an infinite number of steps. But the relevant laws designate it as a physically finite process, and that is all that counts," end quote. So once again, we have the primacy of physics. It doesn't matter if you can invent these stories in the abstract about what might happen if you're moving your hand half the distance and half the distance, half the distance again, and that goes on ad infinitum. That's not what happens in reality. Physical reality is supreme. It reigns supreme. And a simple experiment can refute your great abstract mathematical theory. Done. Skipping a very substantial number of paragraphs now, in fact, a couple of pages, and picking it up towards the end of the chapter now, where we're getting to the real punchline, the important conclusion to this chapter. And David writes, quote, "Once again, we see the inadequacy of the traditional mathematical method of deriving certainty by trying to strip away every possible source of ambiguity or error from our intuitions until only self-evident truth remains. That is what Gödel had done. That is what Church, Post, and especially Turing had done when trying to intuit their universal models for computation. Turing hoped that his abstracted paper-tape model was so simple, so transparent and well-defined that it would not depend on any assumptions about physics that could conceivably be falsified, and therefore it could become the basis of an abstract theory of computation that was dependent on the underlying physics. He thought, as Feynman once put it, that he understood paper, but he was mistaken. Real quantum mechanical paper is wildly different from the abstract stuff that the Turing machine uses." End quote, just pausing there for a moment. And ink is always tricky. We might as well add to that as well. Ink obeys quantum mechanical laws. It isn't just write down what you like and it will remain there in perpetuity. It may, but you can never rule out that something has gone wrong. Anyway, back to the book. David says, quote, "The Turing machine is entirely classical and does not allow for the possibility that the paper might have different symbols written on it in different universes and that those might interfere with one another. Of course, it is impractical to detect interference between different states of a paper tape, but the point is that Turing's intuition, because it included false assumptions from classical physics, caused him to abstract away some of the computational properties of his hypothetical machine, the very properties he intended to keep. That is why the resulting model of computation was incomplete." End quote. Pausing there, my reflection. What completed the model of computation? The quantum computer, the quantum model of computation. David Deutsch's personal scientific work, for which he became so famous, was precisely on this point of regarding tape, if you like, as being as obeying quantum laws of physics, and therefore the quantum computer becomes more powerful, able to do certain tasks much more quickly than what a classical computer can do. David goes on, quote, That mathematicians throughout the ages should have made various mistakes about matters of proof and certainty is only natural. The present discussion should lead us to expect that the current view will not last forever either. But the confidence with which mathematicians have blundered into these mistakes and their inability to acknowledge even the possibility of errors in these matters are, I think, connected with an ancient and widespread confusion between the methods of mathematics and its subject matter. Let me explain. Pausing there. This, of course, comes out of much of David's work on this, where he has spoken at length on what he has called the mathematician's misconception. Well worth looking that up on YouTube, David Deutsch, Mathematician's Misconception, and you'll find his speeches and talks on this, and he's talked to many people about this, and I've produced a number of Talkcast episodes, I'll throw them up on the screen as well, that touch on this topic as well. The mathematician's misconception is that the intuition of a mathematician can be without error, that you can reach these absolute certainties, and that proof can fly free of the laws of physics. That quantum theory has nothing whatever to do with what is being proved in mathematics, or could ever possibly have any bearing on what is going on in proof theory. But that's the misconception. So I'll read that last bit again and continue. David says, quote, that errors in these matters are, I think, connected with an ancient and widespread confusion between the methods of mathematics and its subject matter. Let me explain. Unlike the relationships between physical entities, relationships between abstract entities are independent of any contingent facts and of any laws of physics. They are determined absolutely and objectively by the autonomous properties of the abstract entities themselves. Mathematics, the study of these relationships and properties, is therefore the study of absolutely necessary truths. In other words, the truths that mathematics studies are absolutely certain. But that does not mean our knowledge of those necessary truths is itself certain. Nor does it mean the methods of mathematics confer necessary truth on their conclusions. After all, mathematics also studies falsehoods and paradoxes, and that does not mean that the conclusions of such a study are necessarily false or paradoxical. Let me go back and read that again. In other words, David has said, the truths that mathematics studies are absolutely certain, but that does not mean that our knowledge of those necessary truths is itself certain. Amazing. But it is the next sentence I'm about to read to you where the floor beneath me completely crumbled, the scales fell from my eyes, and I realized, aha. Mathematics, like science, like history, is error-prone. Our knowledge of these domains stands on the same footing. It is a web rather than some sort of edifice that we build, resting upon logical truth that cannot possibly ever be doubted. No, mathematics is special because it studies absolutely necessary truth, but our knowledge of that absolutely necessary truth is not the same thing. Those two things are different. Necessary truth and our knowledge of necessary truth. David goes on to say, and this is the line that I quote most often, one would say I almost well up when I read this now. He says, quote, necessary truth is merely the subject matter of mathematics, not the reward we get for doing mathematics. The objective of mathematics is not and cannot be mathematical certainty. It is not even mathematical truth, certain or otherwise. It is and must be mathematical explanation. Why then does mathematics work so well as it does? Why does it lead to conclusions which, though not certain, can be accepted and applied unproblematically for millennia at least? Ultimately, the reason is that some of our knowledge of the physical world is also that reliable and uncontroversial. And when we understand the physical world sufficiently well, we also understand which physical objects have properties in common with which abstract ones. But in principle, the reliability of our knowledge of mathematics remains subsidiary to our knowledge of physical reality. Every mathematical proof depends absolutely for its validity on our being right about the rules that govern the behavior of some physical objects, be they virtual reality generators, ink and paper, or our own brains. That bears reading again and is undermining of the mathematician's misconception. I can see how it would upset mathematicians and perhaps mathematics students. Study a little bit of physics. But let me read it again. David wrote, quote, "In principle, the reliability of our knowledge of mathematics remains subsidiary to our knowledge of physical reality. Every mathematical proof depends absolutely for its validity on our being right about the rules that govern the behaviour of some physical objects, be they virtual reality generators, ink and paper, or our own brains." Masterful. Beautiful. Let me skip a few more paragraphs, a couple of pages, and bring it home with the conclusion. The conclusion of Chapter 10, The Nature of Mathematics, here in The Fabric of Reality. And David writes, quote, "The fabric of reality, then, does have a more unified structure than would have been possible if mathematical knowledge had been verifiable with certainty, and hence hierarchical, as has traditionally been assumed. Mathematical entities are part of the fabric of reality because they are complex and autonomous. The sort of reality they form is in some ways like the realm of abstractions envisaged by Plato or Penrose, although they are by definition intangible. They exist objectively and have properties that are independent of the laws of physics. However, it is physics that allows us to gain knowledge of this realm, and it imposes stringent constraints. Whereas everything in physical reality is comprehensible, the comprehensible mathematical truths are precisely the infinitesimal minority which happen to correspond exactly to some physical truth, like the fact that if certain symbols made of ink on paper are manipulated in certain ways, certain other symbols appear. That is, they are the truths that can be rendered in virtual reality. We have no choice but to assume that the incomprehensible mathematical entities are real too, because they appear inextricably in our explanations of the comprehensible ones." Pausing there, my reflection on this. Yes, it's been pointed out before that the undecidable propositions or unprovable propositions that Gödel's incompleteness theorem leads to vastly outnumber the number of things that can be proven. The overwhelming majority of mathematical statements, true or false, cannot be proved as such. Now, very few of them are known, and pure mathematicians don't spend time trying to find them because take it as read that there are all these unprovable things. We found some, Gödel found one of the first, and so we also understand that there are vastly more of those than the ones that we can prove. But hey, the ones that we can prove help to solve our problems in the physical world. They're kind of more interesting in a way. I suppose that there are certain kinds of mathematicians who might be interested in finding fun in exploring more unprovable statements. But hey, good luck to them. Many others will be more interested in things that can be proved. Let's keep going. We're at the conclusion now. David writes, quote, "There are physical objects, such as fingers, computers, and brains, whose behaviour can model that of certain abstract objects. In this way, the fabric of physical reality provides us with a window on the world of abstractions. It is a very narrow window and gives us only a limited range of perspectives. Some of the structures that we see out there, such as the natural numbers or the rules of inference of classical logic, seem to be important or fundamental to the abstract world, in the same way as deep laws of nature are fundamental to the physical world. But that could be a misleading appearance. For what we are really seeing is only that some abstract structures are fundamental to our understanding of abstractions. We have no reason to suppose that those structures are objectively significant in the abstract world. It is merely that some abstract entities are nearer and more easily visible from our window than others." End quote. Beautiful. And I might just read, because David at the end of each chapter, of course, has terminology here. And so he has, I don't like to say define, but he explains certain terms that he uses. And the first term here at the end of this chapter is, of course, mathematics itself. So what is mathematics, according to David Deutsch in The Fabric of Reality? Mathematics is the study of absolutely necessary truth. So that's beautiful. It's the study of it. It doesn't mean that you get as a reward absolutely necessary truth, but rather you have some understanding of absolutely necessary truth. And your understanding is flawed, or it could be flawed and faulty and error prone and all that kind of thing. And David also has the word proof that he explains. And he says that proof is a way of establishing the truth of mathematical propositions. Traditionally, he says, it is a sequence of statements starting with some premises and ending with the desired conclusion and satisfying certain rules of inference. But he goes on to say a better definition is a computation that models the properties of some abstract entity and whose outcome establishes that the abstract entity has a given property. That's beautiful. Okay, so that means that the entity that has been computed, that has been proved, has this property that, well, it follows from the axioms, assumed to either be true or assumed for some other reason. You know, these are just what we assume. Using the rules of inference, well, this is what follows as a matter of logic, as a matter of mathematical necessity, fallibly proven by a human being. Now, next time, we'll be finally up to chapter 11, time. Time, the first quantum concept. Now, this is a difficult chapter. I'm going to read through the chapter and I'm going to compare it to especially the work recently of Sam Kuiper's, colleague of David Deutsch, and the Page Wooters construction. This is in part what the chapter is about, and I think Sam's taken things a little bit further even, and I'll speak to Sam at some point on the podcast about the chapter, but not until after I've actually read through the fabric of reality and the quantum concept of time. But I hope you've enjoyed this episode. I've certainly enjoyed bringing it to you. It's, as I say, my second favourite chapter in all of the fabric of reality, with my most often quoted passage there, that necessary truth is the subject matter of mathematics, not the reward we get for doing mathematics. How brilliant, how insightful, and what an evisceration of the mathematician's misconception. Until next time, bye-bye. If you'd like to support what I do here, please sign up at Patreon or go to www.bretthall.org and perhaps send me a PayPal donation. Yes, I'm a little bit like a busker. Until next time, bye-bye.